everyone. So we're going to be doing a new function here, or sorry, a new differential equation. And this one is super important because it comes up on the exam all the time, questions like this specifically, because they're going to involve the function natural log. And College Board loves this type of problem. I would jot this down in the corner. It involves natural log of x. And make a note to yourself here, there are going to be two cases. And that's why College Board loves this, because they can test, like, do you know that there's two cases? Do you know how to solve which case it is? Another thing I want you to remember is, because this thing involves natural log, the graph of natural log of x goes through 1, 0, and if this is E, like 2.7, it goes through E1. And there's a vertical asymptote at x equals 0, VA. And your function looks something like this. And it's always a good idea to draw ln again, because like people forget what natural log looks like all the time. So let me come here. We're going to be graphing. So here's your slope field, 6 times the quantity y minus 3. So here you can see that there looks like there's a horizontal asymptote. Whoa. It looks like there's a horizontal asymptote at, my God, at y equals 3 right here, this red line. So there are going to be, remember how I said there's two cases? It's because you can follow the flow above the horizontal asymptote and go up, or you can follow the flow below the horizontal asymptote and go down. So we're going to be doing actually both cases here, because I really want you to see what happens in each scenario. And we're also going to solve it generally first. So let's find a general solution, and then we'll talk about what a particular solution would look like. Okay. So, another thing that you want to write down here is when you do the antiderivative and you get a natural log, you always are going to have absolute values, remember, because like you can't do the natural log of a negative number just like there's nothing going on right here. So that is why you do a natural log. So it prevents you from ever doing natural log of a negative. All right, so let's separate this thing here. I'm going to move this to the left. So then I have, and then I'm going to also multiply each side by dx, just get this over with here. So then I have dy over y minus 3 equals 6, that canceled, dx. I am going to recommend, if there's just a constant floating around, keep it on the right-hand side with the dx. I generally don't move constants to the left because like this is already going to be complicated enough with a natural log. Keep the 6 with the dx where it's a simple antiderivative. It's just 6x. Okay, that's always going to be my recommendation. At this point, let's do an antiderivative of each side. Well, the antiderivative of the right is going to be a little simpler. It's just 6x. The antiderivative of the left. Okay, the antiderivative of 1 over y minus 3. If you have a variable to the first power in the denominator, the antiderivative of that is going to be natural log. You're used to doing this whenever there is an x. So you would say, hey, this is natural log of x minus 3. You can do it with a different variable. It would just be natural log of y minus 3. And I'm going to put absolute value bars here because I don't want natural log of a negative. I'm not going to do the C1, C2 thing. I'm just going to go right to it and say, hey, we have a constant. I'm putting the constants together on the right-hand side, super C. Okay? So at this point, I've done steps 1 and steps 2. I separated my variables. I found an antiderivative. Let's say that no initial condition is given. So if no initial condition is given, this is very important, and again, comes up all the time. We're going to have two cases here because like I don't know what my curve goes through, so I have to cover both my bases here. So we're just going to solve for y. Like if you don't have an initial condition, you're pretty much ready just to get y on its own. So let's do that. All right, y is trapped with a natural log. So let's see, how am I going to undo a natural log? Let's exponentiate each side. That means raise each side to the power of e. And that leaves us with absolute value of y minus 3. Keep that absolute value. Is e to the 6x plus c. All right, I'm going to highlight this here because this is the part that if you're going to mess up, it's typically with this part right here. And let me remind you of something you know from algebra. If you have x squared times x to the 4th, how do you combine when you have the same base? What do you do with your variables? Like if you're multiplying those bases, well, you add your exponents to get x to the 6th. So check it out. I have one base here, and I have two things in my exponent added. So how would I go backwards? Well, you separate into two different bases multiplied, and they each get one of those terms in the numerator. So instead of 2 plus 4, it's 2 and then a separate 4. So let's do that right here. This would be e to the 6x times e to the c. And put some stars here because I guarantee you're going to get to this point in class and need a little reminder because you're just learning it. So y minus 3. And if this is super C, this is going to be like the ultimate C because like you're taking a constant and exponentiating it. This is just another C. So a constant, e to a constant is just a constant. So e to the 6x times, sometimes people will make it like capital C if these were lowercase c's, but anyway, it's a constant. And I'm going to put a constant up front because that's typically where you would put a constant times an exponential. So this is clearly going to be some kind of exponential curve, and that should make sense because if you picture something going through the slope field, it's going to go way up and look exponential or go way down and look exponential, but like decreasing. All right, so here we go. I don't have an initial condition. So I am going to get rid of these absolute value bars. So I already exponentiated, right? But if I want to get y by itself, I can't really do that until the absolute value bars are gone. So you know how like there's two different curves here? The function could shoot up or shoot down. There are going to be two cases here. And one case is if you have the upper curve. And that would be if the absolute, and make sure you write this down, absolute value bars are off. And then the other case is if you have the lower curve. And just so you know, when I say upper curve and lower curve, the upper curve, so like this would be your upper curve, and then something like this would be your lower curve. And that would be if the absolute value bars, are on. All right, so what would make us have the absolute value bars off? What would require us not to need an absolute value? If you plug in a y value bigger than 3, think about this. If you plug any y value bigger than 3, like 4 or like 5, that would just be the absolute value of 1 or the absolute value of 2. The absolute value bars are not activated. Like you don't have to do anything here. Absolute value of 1 is 1. Absolute value of 2 is 2. The bars are off. Let's talk about what if you plug in a value where y is less than 3. So that could be like 2 minus 3 or 1 minus 3 because 2 and 1 are less than 3. Well, look, this would be the absolute value of negative 1. This would be the absolute value of negative 2. In this case, in order to get 1 and 2, the absolute value bars did something. You went from a negative to a positive. You got the opposite. So I'm going to write this here because I'm going to say the word opposite again. You got the opposite of what was inside. And the reason 3 is the like barrier is because when you look at the slope field, 3 is where you have a horizontal asymptote. So you're either above 3 or you're below 3. All right, so we have to cover both of our cases here because I don't know my initial condition. So I don't know if I have a y greater than 3 or less than 3. So let's talk about what if you have a y value bigger than 3 and your absolute value bars aren't doing anything. You can just drop the bars and nothing happens. Like whether the bars are there or not doesn't matter. And you can just solve for y, case closed. 3 plus c e to the 6x. Done. All right, what if the bars were on and they were activated doing work? So let me rewrite the absolute value bars here. Okay, if you're going to drop the bars, like see how here the bars went away to get to 1, but like it was the opposite. You got positive 1 instead of negative 1. And here to get rid of the bars, you had to do the opposite of negative 2 to get 2. You're going to drop the bars. Like they have to go away to solve for y, but you're going to do the opposite of what it equaled because absolute value makes this the opposite sign. And then you're going to add 3. So then you have 3 minus c e to the 6x. And that's how you're going to get two different types of curves. One of them is positive. One of them is negative. Okay, so again, you turned your bars were working, they're activated, so you have to do the opposite of this side. Also, just so you know, some people, whenever they do this, like whenever they got to this case here and they're going to drop the bars, sometimes instead of putting the negative on the right-hand side, they'll put the negative on the left-hand side, CE to the 6x. Oh my God, sorry, it's messy. And then solve from there. You'll get the same thing in the end because you would like divide by -1, and you'll still get y minus 3 equals -6e to the 6x. So I usually put it on the right-hand side. So that is how, whenever you solve these things, you get two different cases. I'm not going to do the whole solution step out because I don't want to make this one too long, but I just want to show you something real quick. What if I'm just going to set this up. I'm going to choose the initial condition 2 comma 4, which is up here. Hopefully you can see my cursor. 2 comma 4 is in the upper curve, and then 2 comma 1 is in my lower curve. Like, what if I found a curve going through 2 4 and a curve going through 2 1? So let's take those initial conditions, 2 1, and well, I want to do 2 4 first, and 2 1. Remember, you need to plug in your initial condition right after you do an antiderivative. So where did you do an antiderivative? You did an antiderivative right here when ln was still in the picture. So whoop, way down here, moving on down. Whoop, there. I'm going to take natural log of y minus 3 equals 6x plus c. I'm going to plug in my initial condition, 2 comma 4. So that'd be 4 minus 3 equals 6 times 2 plus c. So then you have natural log of 1 equals 12 plus c. Natural log of absolute value of 1 is just natural log of 1. The bars didn't do anything. And natural log of 1 is 0. 12 plus c. And then that means that we have c equaling -12. So c equals -12. So then you can plug that back in and you get 6x minus 12. What if you had 2 comma 1? Then you'd have natural log of 1 minus, whoops, no. Two, whoa, yeah, 1 minus 3, sorry. That equals 6 times 2 plus c. So, okay, I plugged in my x for x, I plugged in my y for y. So natural log of -2 equals 12 plus c. So then you have natural log of 2 equals 12 plus c, and then c equals 12 minus natural log of 2. So then you end up here, y minus 3 equals 6x plus 12 minus natural log of 2. It is very common for your constant to be something kind of ugly, like it's not just a nice number, and you have to carry this through the solution process. It's not just going to go away. If your bars are off, in this case, you would exponentiate, and you still have the absolute value bars in this step. And let me just show you one thing here. This would be e to the 6x times e to the -12. You have to break it up. In this case, because the bars were off, the absolute value bars didn't do anything. Whoa. Then you can just drop them, and you get this. And 3, I'm going to add 3 to each side. So e to the 6x times e to the -12. Okay, so if the bars are off, you can just drop them. You don't have to make the right-hand side negative. In this case, when the bars were on, if you were going to drop the absolute value bars, you'd have to make the right-hand side opposite or negative. And I just want to show you what one of these would end up equaling. This one here was e3 plus e to the 6x times e to the -12. Let me just make sure that's what we got. 3 plus e to the 6x, e to the -12. Okay, so this is an example of the particular solution that is in the upper curve that goes to the order pair 2 comma 4. And if you were to finish solving this one down here and you were to graph it, it would go through 2 comma 1 and be the lower curve. So we're going to be practicing that a lot in class. That'll be good for now. You have a good introduction here, and we will do more Desmos graphing in class, the next class. All right, see you later.